This is HT204, week 2, part 2, and we're continuing the lecture about the basis of energy. So what are the forms of energy? Potential energy. Probably if you did physics, they tell you potential energy is energy that's been stored in an object. If you raise the spin, it has energy now. If you let it go, it will fall. That's basically the force acting on it by gravity. That's potential energy. Kinetic is when somebody's moving. Something's moving. If you throw something, it has a lot of kinetic energy. What about chemical energy? The chemistry of reaction. So when we burn fuel, that's chemical energy. We're combining gas, heat, what else? And oxygen, and you're doing a chemical reaction, that's producing a lot of heat. So you're releasing the energy, that thermal energy inside the fuel into thermal. You can also do another kind of electrical energy by combining things chemically. That's chemical energy. But your battery, that's chemical energy, turned into electrical. You combine whatever two lithium ion with something else. When they combine, they produce electricity and some other new form. Then you charge the battery and you give it some electricity so they separate again. So in your battery, things are like going together and separating again over and over again. And this is how we use chemical energy to produce electricity. Thermal is heat. We get a lot of heat from the sun. And actually we are using the heat from the sun to produce electricity, to heat water. We're not using it efficiently. We could do more. You know, if we capture the entire energy from the sun on one day, it's coming on Earth, that is enough to sustain humanity for over 100,000 years. Okay, imagine if you have you capture all the sun radiation on Earth in one day, it will last the entire humanity needs for over 100,000 years. Of course, that's hypothetical because it's not possible. You cannot capture the energy in the oceans and stuff. But this is how much energy the sun is giving us. So the more we can capitalize on that, and so far we're only focusing on solar energy as photovoltaic, which means the light. We are just starting to capture the sun heat. Of course, that's not always possible because some places don't get a lot of sun rays that are hot. But if you go to New Mexico, California, they have almost 15 megawatt plants in the middle of the desert. It's very amazing. It has 5,000 mirrors that focuses sun rays in one tower and makes energy. So they are doing that. In Spain, Italy, in a lot of places where there's a lot of sun, you can do that. There are plants who do, yeah?
They're everywhere in California.
Because the sun is available there. So you can use that. So 99% of our energy comes from the sun. What about the other 1%?
From the Earth.
From the Earth, yeah. From the Earth cooling off from the Big Bang. That's a long time ago. That's very interesting. Okay, moving on. So this is what we will need to understand a little bit. Probably you'll need to use the term therm. Therm is 100,000 BTU. That's a therm. You'll see that when you do industrial programs. Kilowatt. I surely hope that you know what kilowatt is because you're paying for it. When you look at your power bill, they will charge you for kilowatt.
You said therms was 100,000 BTUs?
100,000 BTUs. Kilowatt, it's related to watt. Watt is 1 volt going over at 1 ampere rate. So it's a kilowatt. Kilo is what? 1,000?
Yeah.
So 1,000 watt. And that's what you pay for. How much is a kilowatt in New England, in Massachusetts?
21 cents.
29?
21.
21, yeah.
Varies.
Varies. I see 15, I said 21. Last summer it was very expensive, yeah.
I just saw a report from days ago that in January, the average rate was about 22 cents.
Yeah,
in Massachusetts.
yeah, they increased the rates. That's why, okay. It was 15 2 years ago, now it's 21. Okay, great. So 21 cents. So probably there's a lot of, that's why they have mass save now, I see. Anyways. So kilowatts, it's what you pay for. Or sometimes they charge you for the volume of oil and gas. So usually when you go look at your gas bill, they're charging you per therm. look at the gas bill.
Really?
They don't charge you per gas volume term, because you don't know what kind of blend they have, what kind of gas and you gotta go with whatever they tell you. So
Well,
it's
how,
gonna be a
how do
term.
they measure their therm?
Huh?
How do they measure the therm?
They,
Do they just throw it in a?
no, they have
burn?
actually few scientists who actually will see what kind of blend they have that day, and they'll say based on the volume we're pumping, this is how much BTU is in it. And there is a way to measure it. Volume of oil or gas, that's also another measurement of energy. So if I have 1 gallon of fuel oil, how many BTUs is in that? In one oil of one gallon of fuel oil, how many BTUs? Yeah. Don't look. Give me a number.
10,000?
Nah. More.
1,000?
More.
Oh, wait, what was the question?
100,000?
More.
A million?
No. 138. 138 BTUs.
In 1 gallon?
1 gallon, yeah.
I heard that if the human was able to consume a gallon of gasoline, that would allow us to live, or we could survive on that for like 40 years or something like that, because of how much energy is in
Actually,
a gallon.
you know, I did a calculation. If we were to compare the efficiency of human being to a Kawasaki Ninja, human being is more efficient. If you're on a bicycle doing the work, based on displacement and work, and we used peanut oil, not gasoline. Come on, you won't kill somebody. Peanut oil as your fuel, and the Kawasaki Ninja using gasoline, and we do the same thing. Human being is more efficient in consuming that than a Kawasaki Ninja, but Kawasaki Ninja is very fast. Yeah, yeah.
So according to your BTUs and therms, 1 gallon of fuel oil is 1.38 therms.
How much? Yeah, yeah.
Okay.
Yeah. So we can convert all forms of energy from one measurement to another. You're gonna see BTU, you're gonna see watt, you're gonna see calorie. They all convert again. That's how we did. This is how Chris got the idea of how would that compare to human being consuming oil. So we can compare it because energy is all it's all going to be changeable. So how for calories? If you go to Europe and you look at food, they don't give you calorie. They give you kilojoule. So they have different measurements. They will say calorie is 2,000, but kilojoule as energy because they try to make things uniform a little bit. So there's kilojoule or kilocalories, and so you can convert that. This is another good thing to show you something that all units made up are basically 4 kind of units, a combination of those units, which is meter for distance, second for time, kilogram or kilogram for weight, and coulomb for charge. Everything else is just a combination of those two. So 1,000 watt is 1 kilowatt is 1,000 watt. A watt is joule per second, which is Newton per meter, which goes to kilogram per meter per second square. This you don't have to know this. I'm sorry. I guess I have to share that with you. Because I think it's fascinating. But I think it's blackout. So the energy transfer, the work done, move an electric charge of 1 coulomb through an electric potential. Difference is 1 volt. So this is the definition of volt. It's basically how much energy is done to move 1 coulomb of charge at some rate. Okay. What do you need to remember in here? What's the term? What's a kilowatt? And volume. Forget the other stuff. But it's good to know. Just to give you a concept of how things are connected and how they can transfer from one form to another.
What's the volume then?
The volume of oil of gas is, for example, this one gallon of oil. So sometimes the volume can give you, they can give you a measurement of oil, of energy for volume. Either cubic feet of gas, volume of gas, and just assume what's in it. Good? Units of energy is from your book. This is the most common one, BTU. British thermal unit. Of course, it's only common, actually it's common everywhere. Somehow in the HVAC and AC is BTU stuck, even though the entire world's trying to go into kilowatt. BTUs became just very, very common. I don't think it will ever change. It's always going to be 1,000 BTU, 5,000 BTU, which is a British thermal unit. What is a BTU? It's the energy in one matchstick. It's the energy required to heat
1 pound.
1 pound of water, 1 degree Fahrenheit. So, I don't know who came up with this kind of measurement, but whatever. It's like you know what's a foot?
Yeah, it was
12 inches.
the
Was King Henry's
yeah, the
foot.
kings and
So we're living with King Henry's foot forever. He was immortalized by his foot, which is 12 inches. That's a big foot, let's say. It was 12 inches. So that's his foot. And a lot of those actually had to do with imperial stuff. So anyways, well, it is imperial. So watts is joule per second. So again, if you notice, all this has time unit, and what do you see the distinction? Power and energy. So energy is different than power. What is power?
What?
Energy over time. So you have horsepower, you don't have horse energy. So horsepower is how much you spend that energy. I'll give the example between the Ferrari and the Corolla. They use the same energy, right? The same energy. Well, sorry. Ferrari probably uses octane 105. Let's go a little bit lower. A Porsche uses same octane level, 87. Okay, and a Corolla. The energy inside the gasoline is the same. The power, of course, the Porsche has more power. So how fast do you spend that energy?
A lot.
Yeah. So a Porsche probably going to be 12 miles per gallon. The Corolla will give you 40. So that's why it's efficient. So the power has to do with time you spend that energy. The energy is the same. So energy is a quantity. Power is a rate. Whenever I say rate, is per time, per second. So if you don't see energy unit is BTU, this is BTU per hour. Watts is joule per second, kilowatt per hour, and so on. Same thing. If you got horsepower, it's 33,000 foot-pound per second. Horsepower you'll see for boilers. Industrial boilers, they use horsepower. Again, it's another measure of power. These are all in your book. What you need to know is that the BTU and watts, we're going to use those interchangeably. BTU is always for AC and boilers, which is funny because the AC will give you BTU, but the input is going to be kilowatt. So somehow you have to know the efficiency. Okay. For HVAC, we have BTU, the energy in one match, energy to raise one temperature, 1 pound of water by 1 degree Fahrenheit. And we have the therm, which is 100,000 BTU. We all get that. What other forms of energy we have? Give me name of energy.
torque.
Torque is power, is force. It's a force. It's energy
Yes.
per, yeah. Force per time. So that's power. What about, what is torque? That's good question. It's getting into electricity. Torque is a twisting force. Twisting force has to do with the armature of the force. So what other forms we have for energy? BTU, calories, kilojoule. Okay, another concept. Is there such thing as coldness?
No.
Coldness.
Yeah,
Absence of heat.
it's absence of heat. It's only heat. What is the absolute absence of any kind of heat?
Absolute zero.
Cold, which is what?
Kelvin?
It's in Kelvin. It's 0 Kelvin, which is minus 273 Celsius. That's when that's absolute zero in outer space when everything stops completely.
It's just
Absolute-
theoretically impossible to reach. Because there'll always be heat
No,
anywhere in the universe.
They do it in a lot of conditions.
But they get it close. not,
Huh?
they get it close, but not perfect.
Absolute zero. I'm not sure. Yeah, you get very, very close, but not absolute
Yeah.
zero. Okay, what else? So, what is thermodynamics again? We talked about that. Is the branch of physics that concerns with heat and temperature and their relationship to energy and work. So, look, heat and temperature. Heat is energy. Temperature is a measure of heat. What kind of heat? Sensible related? Sensible heat. Relationship to energy and work. Energy is quantity. Work is the result of using energy over time. So your car has energy in it, but it's not. If the car is idling, it's doing some work. No, there's no displacement. The car did not move, so you're just burning energy for nothing, and the power is very low. When your car accelerates, that's when you use energy and power. Okay. So we use thermodynamics all around us. It's in your car, it's in your boiler, it's in your heating the house, it's in your cooking, it's when you go to the gym and work out. It's all around us. It's just a different way to look at it. So when you go and look at your boiler, at your house system, probably you're gonna have different perspective. Okay, what's happening here? What's being burned? Where's the energy coming from? Where is it going? Where is it leaking? So think of all these little details here and there. So, just to repeat, it's the first law of thermodynamics and the conservation of energy. I would say 99% of the energy comes from the sun. So sun, living organism, fossil fuel, heat, work, heat and landfill, and that's where we are breaking the cycles, and that goes round and round. Over time, the heat and landfill will transform into something else, but it's going to take a lot of time. So everything is cyclical. Second law of thermodynamics. I think that's enough, huh? Jason's giving me the look. Okay, I'll stop here.